Swayam Prabha. Digital India. Educated India.
Thank you. You probably did not hear what I'm going to speak about. I'm sorry I could not share the title with Dinesh earlier. It's just been a hectic couple of weeks. I'm a cosmologist. Can you comment about what cosmology implies, what cosmology means, what cosmology deals with? One at a time, one at a time. That is not on? Okay. Someone else? Okay. We'll hear other views. Study of the? Cosmos. Absolutely. So the point is, we are not interested in astronomy, which is anything outside the Earth. Okay. It of course, and the universe encompasses the Earth as well. We are not interested in cosmic rays. That is one aspect. And what was the other answer? The different states of the universe. To some extent, it is true. We are interested in the physics of the universe as a whole, and that's what cosmology is. Do you know what is the current model of cosmology? Do you know the name of the current model of cosmology? There is something said cyclic cosmology, Big Bang cosmology. Anything else? May not be. I'll clarify. Yeah. Any other comments? Any other suggestions? I'm asking, what is the current model of cosmology referred to? It has a popular name. It has a more standard name, and it has a popular name. I would like to know whether you know the popular name. Technically it is referred to just like you have a standard model of particle physics. I'm sure, I would imagine someone have talked about the standard model of particle physics. There is a standard model of cosmology, but there is a very popular name. Someone mentioned it. There is even a famous American sitcom. It's called The Big Bang Theory. And my goal in today's talk is to explain to you, within the limited time available, why we believe that the universe is described by the hot Big Bang model. You should understand that virtually every civilization historically has its own model of cosmology. But something drastically has changed over the last 100 years or so. We have taken great strides in the field of observational astronomy, which has led to this, discovery first of the expanding universe. Something I will refer to as the cosmic microwave background, something that is referred to as the cosmic microwave background. You would have heard about the fact that the universe is accelerating and therefore it is dominated by dark energy. And there are CMB, what are known as cosmic microwave background. I will refer to it repeatedly as the CMB. Please keep this in mind. There are what are known as anisotropies in the CMB, which are being measured with greater and greater precision. All these observations has led to this, what is known as the standard model of cosmology, and it is, in the popular parlance, it is referred to as the hot Big Bang model. What I want to emphasize is that in contrast to what happened before 100 years or so, we have a scientific model of cosmology which is driven by astronomical and cosmological data. That's what I would like to I would like to tell you the story of why we believe in the hot Big Bang model over the next couple of hours. You're welcome to stop me and ask questions. If I have a simple answer, I will provide that then. Else, we'll wait towards the end of the talk for me to answer in some more detail. In order to, I'll just come to you in a minute, okay? Before we proceed, we need to know what the universe contains. So I will start with a survey of the universe, but there is a question even before that. Please go ahead.
Sir, can you just repeat the difference between astronomy and cosmology?
So astronomy is, there was suggestions that we are studying cosmic rays, and there were suggestions that we are studying something just beyond the earth. Astronomy is observing anything which is celestial, beyond earth, as was suggested. Okay? When I say cosmology, I'm interested in the physics of the universe as a whole. I am not interested in the physics of some stars here, some galaxies here, or even collections of galaxies. We are interested in the physics of the universe as a whole. In order to know what does the universe contain, I will have to start with a survey of what the universe has. I will do that. Okay? In summary, astronomy is just observing the universe. Okay? In contrast to other aspects of physics, I can't carry out experiments with my world, with my universe. I have to observe it. I observe. That is astronomical. There is a subtle difference between astronomical and cosmological data. When you try to understand the behavior of a star here, a galaxy here, you have astronomical observations. But there are certain observations which tell you about the universe as a whole. Then you refer to them as cosmological observation or cosmological data. And similarly, if you are trying to understand the physics of a star, physics of a galaxy, you are interested in what is known as astrophysics. Okay? And the physics of the universe as a whole is what we refer to as cosmology. Is that clear now? Sorry? I need to know how the universe, the whole, what does the universe contain, how it came into be, how is it evolving. No, we have to look at all places. What I am trying to say is that if you look at this particular corner of the sky, all right, and understand the behavior of stars or galaxies, that doesn't tell me about the complete universe. Okay? It will become, maybe you need to be a little patient, it will become clear after a few slides what I mean as the physics of the universe as a whole. Okay? As I mentioned, what we need to know is what the universe contains. Since many of you may not know what all the universe contains, okay, whatever we have observed, that is what I mean. I will start with a survey of the universe. What we will do is that as we see around, you see a star here, you see we are part of a galaxy, which I'm sure you've heard of. And there are many, many galaxies, and there are clusters of galaxies. And in fact, there is a hierarchy of cluster structures that we talk about. We are part of a solar system. We are on a planet. The planet is part of the solar system. The solar system is part of the galaxy. And I will tell you the galaxy is part of some small group of galaxies, and that in turn is formed part of a cluster of galaxies, and there are clusters and clusters of galaxies, and these whole thing forms our universe. Okay? And evidently, when I say structure, when I mean structure, I'm talking about structures on large scales. I will explain what that large scale is. This is the division between astronomy/astrophysics and cosmology. Okay? What is the scale at which you are observing? Evidently, if you are focusing on the dynamics of the earth, it's not cosmology. Or even if you focus on the dynamics of a galaxy, it's not cosmology. You are interested in truly large scales, and I will try to explain what that large scale is. So the structures, you would have seen something known as the distribution of large scale structure. I will show some pictures of it as we proceed so that you can have a picture in your mind. To understand our universe, there is no smoothness. There is galaxies and clusters of galaxies. But in order to simplify, mathematically describe our universe, it happens to be simple to assume that there is a smooth universe. I will explain what is smoothness. We assume that is a smooth universe, on top of which there are small deviations. Think of a plane, and there is a smooth distribution of matter, density in the universe. Okay? And something did induced some changes, and it started, the smoothness got disturbed. And when the smoothness gets disturbed, gravity plays a role. Gravity is always present. And what will gravity do when there is smoothness that has been disturbed? It will start, gathering matter. And that's how structures are supposed to have formed. So the first part of the story is about, which I will try to cover in the next 40-50 minutes, is to understand the composition. What does the universe contain? And how did it evolve? What is this Big Bang that we are talking about? Why do we believe there was a Big Bang? And then we see this hot Big Bang model is not very good. It has its problems. I will try to explain in the second lecture what are the problems. All right? And I told you that we are going to assume that the universe is smooth. And I will give you reasons to believe, observational reasons, okay, to believe that very early in the universe, it was indeed smooth. That is, the energy density was smoothly distributed. But it's not today, right? You have a galaxy here, you have a galaxy here, a cluster of galaxies. There is empty space in between, all right? How did this? So the challenge is to understand why is the universe so smooth on one hand. At the same time, how did these structures, these galaxies and clusters of galaxies form? There is an idea called the inflationary scenario that is introduced to induce these deviations from smoothness, which grow, as I mentioned, due to gravitational instability. Gravitational instability implies, just that if you have a smooth distribution of matter in this room, and the moment I add a little mass here, it's smooth initially. The moment I add a little mass here, what will happen? Due to Newtonian gravity, all the other mass will start getting attracted towards this large mass. That's what gravitational instability is. So if I have smooth distribution of matter, the moment something causes some fluctuations, right, it will induce what is known as gravitational instability. And that is why these galaxies and clusters of galaxies that are supposed to have been formed. So I will explain what are known as perturbation. Do you understand the concept of a perturbation? When, I am perturbed, what does that mean? Sorry? You are disturbed, that's right. You are gently disturbed, not greatly disturbed. A perturbation in physics means something which is a small disturbance. You may have thought of the simple harmonic oscillator, right? X cube potential, right? X squared, potential, right? It is described. If I add a small plus alpha x cube, where alpha in some units is a very small number, then you call it as a perturbation. So what we will see is that there were very tiny perturbations in the early universe, okay? And then due to the gravitational instability, which I have repeatedly mentioned to you about, okay, it grows into the structures that we see around us today. And all this leads to the standard model of cosmology. The cosmologists don't refer to it as the Big Bang model. It is, it is in the popular parlance. In fact, the name was given in a derogatory sense. I will comment about it much later, okay? And what we refer to it as the standard model of cosmology, and close with some, useful references for you to read. I should mention, there are aspects of this story which will be difficult for me to convey. You need two things, to understand cosmology completely. You need to know something called theory of fields, theory of electromagnetic fields, and there are other fields as well. And you need to know what is known as the relativistic theory of gravitation, which is general relativity. In order to appreciate cosmology completely, you need to know this. To derive all the expressions I may have, I have tried to limit the number of equations I have on the slides, okay? You will need that theory in order to appreciate it completely, but if you are curious, you can speak to me. I can refer you to some textbooks where you can broadly understand how these equations arise. Let's proceed. So we start with a survey of the universe. Where do we begin? We begin with our galaxy. This is a picture of our galaxy taken from outside the galaxy. Do you believe that? Why? We have hardly gone beyond. Voyager, I believe, is one of the earliest satellites sent into outer space. and it has hardly gone beyond the end of the solar system. So this is a picture taken by the Cosmic Background Explorer, COBE. We will encounter this satellite later. Okay, it is a picture of our galaxy. What it did was that it had an infrared camera, and it just exposed the infrared camera to all regions of the sky. And it arrived at this picture. So what do you see? You see a flat pancake or a dosa, but it's not quite a dosa, but it has a bulge in the middle. So it becomes a appam, right? It's not a dosa. It has a bulge in the middle. In fact, what you have is what is known as a spiral galaxy. We are not able to see the spiral arms because we are in one of the arms of the galaxies. We are in a plane of the appam, and therefore we are not able to see. And there are a few things which I want you to learn about this. We are not so much worried about the galaxy. Very soon, you will recognize we are not only Earth, not only the solar system, even our galaxy is some tiny irrelevant speck in the whole universe. Okay, so we are not interested in our galaxy as such, but it is just to help you understand some numbers. The size of the galaxy, the diameter approximately of this disk is about 45,000 light years, or we will talk about a strange unit called a parsec. It's about a 3.26 light years, and I explain why this number comes about, and what it is about 15 kiloparsec. You typically say that the size of the galaxy is 15 kiloparsec. You don't need to write this down. I can make these slides available somewhere. You can download and look at it whenever you want. And there are some useful links as well, which you can peruse. Okay. So what do you have? One of the things I want you to appreciate is that it contains about 10 power 11 stars such as the sun, right? This object you see here, M with a circle and a dot in the middle, is the mass of the sun. The mass of the sun is about 2 times 10 power 30 kilograms. So what you see is that it doesn't work here. Okay, it is about 2 times 10 power 12 solar mass. Notice what you have. It has about 10 power 11 stars, but its mass is about 10 or about 20 times larger than all the stars put together. Can you guess what it implies? No, that's not what it implies. Yeah, there is some other strange matter present in the universe, okay, present in the galaxies. We will come to that. There is matter other than matter which shines like the stars, and we will talk about it as we proceed. And what is this? Why are we talking about this 3.26 light years? I'll come to you in a minute, okay? Let me just explain this idea of a parsec, which is 3.26 light years, okay? So what you do is as follows. I presume you know the idea of trigonometric parallax. It's a simple idea. So this is the average radius of the Earth around the sun. It's referred to as 1 astronomical unit. You look at a star 6 months apart, say in July and January, and you take a picture of the star, which is a nearby star with respect to farther away stars. Okay, so this angle is some P, and this distance is D, and using basic trigonometry, and if you measure this angle, right, you can measure the distance to the star. And you can do a simple algebra, okay, and what you find is that, if P is 1 second of arc, what is P? It is this angle here. The angle subtended by the star 6 months apart with respect to farther away stars is 1 second of arc. Then you can show using basic trigonometry that it corresponds to about 3.26 light years, and I assume you know what a light year is. It's the distance traveled by light in a year. So it is because of this strange, distance, namely the astronomical unit, that is the radius of the Earth's orbit around the sun, we have this unit of 3.26 light years, and we will talk in terms of kiloparsec. 1 parsec is about 3.26 light years. We will talk in terms of kiloparsec, and very soon in terms of megaparsec. Okay, so we go beyond our galaxy now, and I can quickly address the questions that were asked. Yeah. Very good question. We'll come to that. Okay. I will not be able to, I need to complete the story. Okay. So I have enough slides. So I may not be able to answer everything in this, within this 2 hours. I'll be glad to be available during coffee break or lunch break so that I can answer additional questions. You had a question. So you can measure using something known as rotation curves of galaxies. Okay. There is one slide which we come to it. In fact, that is what it tells us about using Newtonian physics and rotation curves of galaxies. Okay, galaxies rotate, and you can look at the rotation curves. Okay, what it means is that you can look at the spectrum of stars, look at their Doppler effect, measure their velocities, and using Newtonian physics, you can estimate what is the mass of the galaxy. Yes.
Sir, in the calculation which you did for the for showing that the mass of the galaxy has other stuff which is not accounted for by the stars, the sun is a very small star comparatively. So, like, sorry, the sun is a smaller star.
No, we are talking about yes. I said it contains about 10 power 11 stars. We didn't, such as the sun. So you typically say that, I am not saying all stars are like the sun, There are about 10 power 11 stars. On the average, they have the mass of the sun, but the mass of the galaxy is more than that. Okay? All right. So let me proceed with the story. Okay? What do we have? We are going beyond our galaxy. And as I mentioned, there is a hierarchy of clusters in the universe, hierarchy of structures in the universe. As you look around, there are many other galaxies, and we form a part of something known as a local group of galaxies of about 30 galaxies or so. The galaxy on the left is the Andromeda galaxy. It's called M31. If you have seen through a telescope, you may have seen that as a blurry object in the sky, provided you go far away from Chennai. Okay? And there are other galaxies. This is called the Triangulum galaxy or M33 galaxy. Remember this M33. I talked about rotation curves of galaxies. You had some questions. There is a slide much later, where we come back to this galaxy. And notice what is the distance to the Andromeda galaxy. The nearest galaxy, we actually have very tiny satellite galaxies, circling the Milky Way, all right? But if you look at the nearest largest galaxy, that happens to be the Andromeda galaxy, and look at the distance to the galaxy. It's about 700 kiloparsec or so. So it's largely empty space between our galaxy and the Andromeda galaxy. 700 kiloparsec is about 2 million light years or so. Okay, so there are varieties of galaxies in the universe. I will not be able to, discuss properties of those galaxies, and importantly, we are not interested in the properties of these galaxies. We are interested in the properties of the universe as a whole. There is a disk galaxy. This is very much like our own galaxy. There is a galaxy which contains a barred spiral. It's not just a spiral like this. Okay, but there is a bar, sorry, I went in the wrong direction. There is a bar in between as well. So there are varieties of galaxies that make up our universe. And as you could have imagined, there are clusters of galaxies. What I talked about earlier is our local group of galaxies, and this is known as the Virgo cluster. So you can think of a small local group of galaxies which is part of a huge Virgo clusters of galaxies, which is the size of the Virgo cluster is about 20 megaparsec. Please note, we are talking about really large distances now. 20 megaparsec. Mega, I presume you recognize what it is about 10 power 6 parsec. And as you may have guessed, there are many such clusters of galaxies. You have hundreds or thousands of galaxies extending over even 100 megaparsec or larger. So what do you see? As you see around the universe, there are higher and higher clustering of structures in the universe. What does the universe contain on this larger scales? These are one of the deepest views in space. This is 30 years old. There is a much more recent picture. Unfortunately, I haven't had the time to include this. This is a picture taken by the Hubble Space Telescope. This is a very famous picture, but it is 30 years old. And what I want you to appreciate is that each extended object that you see here is a galaxy. So as you see around you, you have galaxies and galaxies and galaxies, and they are in the form of clusters and hierarchy of clusters, etc. If you want to understand the universe as a whole, you need to carry out a survey of the universe. And one of the earliest such surveys is called the 2-degree field redshift survey. This object is the Keralite Appam that I talked about earlier. It's our galaxy. So what astronomers did was that they took 1-degree field of the sky north of the equator. This is the galactic equator, all right? And they took 1-degree field south of the galactic equator, and they invested some powerful telescope and observed galaxies as far as they can see, okay? As the resolution of the telescopes allowed. It is very much like, taking the census of a country. We are interested in the galaxies present in the universe, and the image they came up with it is as follows. Don't worry about the different colors, they correspond to different galaxies, but that is not so important for our story. These are the 2 different directions, one north of the equator and one south of the equator that was observed. And what you find is galaxies and galaxies and galaxies in the universe. And one of the things you notice is that as you go further away, the galaxies thin out. Can you tell me why this could happen? Can you guess why this could happen? Sorry? No, you are jumping the story. You can see there are many galaxies present here, but as we go further away, there seems to be lesser number of galaxies. No, it's very simple. No, then you would have seen them as well, right? It's simple. You have a telescopes of a particular resolution, all right? It picks up the brighter galaxies, it doesn't pick up the less bright ones. That's all, as simple as that. So that is not the true universe, it's a property of the limit, it's a limitation of the telescope. But now you draw a circle. I've been saying that I'm going to assume that the universe is smooth. I'm going to use the words homogeneous and isotropic. I will explain that. It's not difficult to understand. Homogeneous means same in all locations, right? Independent of if this, there is distribution of students in this room, okay? Until this point, as far as I'm concerned, it seems fairly homogeneous. But there is a scale involved. If I draw a circle like this, there is only one student involved, right? And if I draw a circle like this, there is no student. Evidently, there is no homogeneity. But if I draw sufficiently, yes, there is a gap which has been left behind for the camera. But imagine, it's reasonably smoothly distributed. So on a suitably large radius, independent of where I place the circle in this room, the number of students inside that room will be the same. Fair? Then I say the distribution of students in this room is homogeneous. But there is a scale involved, a length scale involved, a radius involved. If the radius is too small, I am falling in a gap between the two students, and evidently there is no student there, and you can't claim that. So in the same fashion, I can draw a circle here, and over this circle, the amount of matter present within the universe, within that circle rather, seems to be the same independent of where I place the circle. And the size of this circle, okay, actually in the 3-dimensional universe, you have to place a sphere, okay. If you have a sphere of radius of the order of 100 megaparsec or so, 82. Please remember, in physics, there are always some uncertainties involved, okay. On scales of the order of 80 to 100 megaparsec, independent of where you place the sphere in the universe, the amount of matter within that seems to be the same. In other words, you say, just like the distribution of students in this room, I'll come to you in a minute, okay? The distribution of this room is smooth, provided I cover at least this part, which is roughly the width of 2 students, say, a meter or so, okay? But on smaller scales of 30 centimeter, there is a gap between the 2 students, and evidently it's not homogeneous on those scales. So one finds that the universe is homogeneous on scales of the order of 70 to 100 megaparsec. Okay? This is the manner in which we talk about a smooth universe. It is smooth over those scales. The other point is that it is isotropic. What does isotropy mean? Sorry? No, we don't have to talk about entropy. We are just talking about distribution of matter. Okay? No. You are mixing, isothermal and so on. No. You are mixing a completely different concept. Okay? It's a simpler idea. What is isotropic? Same in all directions. That's all. Okay? So in other words, independent of, there is no special direction in the sky. There is no special directions in the sky. So the universe is homogeneous. I hope you understand what it means. I take this sphere of radius of the order of 100 megaparsec. I place it different directions of the sky, different locations of the sky, not directions, different locations. It's the same. What is the same? The amount of matter inside it. Okay? And I place it in different directions of the sky, and the amount of matter is the same. So then I say it is isotropic. The universe happens to be homogeneous and isotropic. Yes.
Yes, sir. So in this case, we are assuming the universe to be spherical in nature. We don't know the actual shape.
I don't know what you mean by there is a distribution of matter in the universe. What do you mean the shape of the universe? I have no idea what it means.
When we take a radius, you said that
I take a radius. I can take a cube. Okay? I can take a cube. That is just a matter of distinction. Okay? I mean, I'm not interested in I don't know. I'm observing the universe. I'm describing it. I'm interested in asking questions like, what is that? I have observations. Why do these objects have turned out to be the way they are? Why do I have these objects? Why do they have these certain properties, etc.? That is what we want to know. Yeah? I don't know what you mean by the shape of the universe. It's not like a ball inside which we are thinking the universe. In fact, we don't even know whether the universe ends, where it ends. We don't know about those things.
Sir, if the universe is isotropic, why is the Milky Way, for example, a disk and not a sphere?
But I'm talking about the universe. I'm not talking about a galaxy. You're mixing a universe and a galaxy. I hope you understand. We are not interested. Each of these objects is a galaxy. Okay? And what we have done is, due to the limitation of our telescope and the availability of telescope time, we observe two different directions of the sky. Okay? I'll quickly show you a movie where we have been able to observe in many different directions. What you will find is that, it is indeed homogeneous and isotropic.
Sir, we don't know the limit of the universe, so for our convenience, we're assuming it to be homogeneous? Could we say so?
It is possible, when I talk about a universe, I'm talking about an observable universe. Okay? What lies beyond? I don't know at this stage. I'm not going to comment about it. I'm a physicist. I'm not a mathematician. Questions? So let's proceed with the story. Okay? What I showed is an older survey. I'm going to show you a much newer survey. Okay? In fact, even this is an old survey. It's a decade old. I need to update my slides. Okay? So this is called the Slow and Digital Sky Survey, but for our purposes, it does a good job. Let me see whether this link works. Okay, it doesn't work, so all right. So this is a picture created by this Slow and Digital Sky Survey. What it does is that it starts, I presume you saw where it started. This was our Milky Way galaxy. It started with our Milky Way galaxies and it goes out. And there will be two yellow grids, circular grids, spherical grids in fact, that you will see as the movie runs. The speed of the movie is irrelevant. Okay? So the first thing you will see is that on small scales, it's largely empty space. But it's only on very large scales. You now know what I mean by very large scales. There are adequate number of galaxies in the universe. The two grids, yellow grids, spherical grids that I talked about will appear at 1 million light years and 1 billion light years. Okay? At the end, towards the very end of the video, you will see a pattern appearing in the sky that also will play a crucial role, in our story. Let me play the movie for you. So we are going further and further away from our galaxy. The speed at which it's moving away, it is not relevant for us. And this is the first grid at a distance of about 1 million light years. Now, what do you expect to occur? You expect Andromeda galaxy, which is at a distance of about 2 billion light years. That's the nearest big galaxy, very much like our own galaxy, which will appear. It should appear sometime now, unless it has already gone. And there it is. Okay? That's at a distance of 2 million light years. And we go farther and farther away. Okay? And what the Slow and Digital Sky survey did was that, in contrast to the 2DF survey, the earlier survey, which observed only 2 different directions of the sky, the Slow and Digital Sky survey observed in many different directions of the sky. The universe is largely empty space. That's what you see on small scales. But if you look at suitably large scales, you're talking about hundreds of megaparts. You begin to see more and more galaxies in the universe. Okay? There are many, many galaxies. And as I mentioned, it observed in different directions of the sky. Right? Don't worry again about the different colors. Okay? What you see is indeed true. What they have done is that they have observed different directions and they're rotating to show you the different directions of the sky they have observed. And it is clear that if I draw a circle anywhere here, there is a sense of homogeneity and isotropy. There doesn't seem to be any special directions in the sky. And after some time, there will be, you won't get to see the galaxies, partly because of the limitation of your telescope. There are brighter, better telescopes observing the galaxy, observing the universe today. And then, towards the very end, there's still a minute left. Can you see this pattern here of blue, red, yellow, and green dots? And they correspond to something I refer to as the CMB, or the cosmic microwave background. All right? We can't see beyond this point for reasons that I will explain later. And this CMB that you see plays a very crucial role in our understanding of the universe, and in fact, to this name of the hot Big Bang model. So let me go back to my slides. Okay. So we have seen what the universe contains. Now we need to understand, in terms of galaxies and clusters of galaxies. Okay. But we need to know in a microscopic level, what do these galaxies contain? Do they contain ordinary matter? Do they contain radiation? Do they contain matter? What do we mean by matter? Sorry? Anything that has mass, okay? More relativistically, you will say anything that has energy, okay? So in some sense, radiation is matter, but cosmologists, we like to distinguish radiation, which is light, right, with matter that you and me are made of. And in fact, what cosmologists will do is that what you and me are made of are baryonic matter. Okay? They will not distinguish. Baryons correspond to protons and neutrons, while electrons and other objects are referred to as leptons. But that particle physicists make the distinction. Cosmologists don't bother about it. Matter we know, where we can create an experiments, make them collide and so on, we refer to as baryons. So we are all made of baryons. I already mentioned there is another type of matter in relating to a question. Dark matter. There seems to be some dark matter. There is I need to explain to you why we believe there is dark matter. All right? There is matter that we know of, that you and me are made of, right? And there is certainly radiation. So where do you see the radiation? Where does the radiation emit? What is the origin of this radiation that you see? Huh? Stars, galaxies, right? That's how I see these. And you would think that the radiation in the universe is dominated by the radiation emitted by the stars in the various galaxies. Not so. Not so. Okay? It's dominated by this object that I mentioned called the cosmic microwave background radiation. So there is matter in the universe, matter involving baryons. Okay? There is radiation in the universe. These two are clear. Okay? In fact, it is not clear that the radiation is dominated by the CMB. That has to be observed, argued, But strangely, observations point to the fact there are additional matter present. There is cold dark matter. Dark matter is because it doesn't interact with light. In fact, it doesn't interact with any object that we know. It interacts only, its effects are seen only through gravitation. I'll come to you in a minute. Just bear with me. Okay? And there is something even beyond, something even more bizarre called dark energy. Okay? All these are present in the universe. We need to understand the composition of the universe. And if we know the composition of the universe, we know the evolution of the universe. You had a comment. Go ahead. Okay. All right. Okay. So, just bear with me as I try to complete a sentence. I will come to you. Yeah? All right? If you just wait for me to complete a sentence and ask a question, or if you ask a question, I will complete my argument and come and answer your question. But when we see around our universe, does it seem to change? Does the universe change with time? Well, it doesn't seem to. What is changing with time? The galaxy is where it is. Why? Someone is saying that the universe is expanding. Okay? Yes, it is. It is changing with time. Right? So, we need to understand the composition and the evolution of the universe. As you would have naively imagined even in Newtonian physics, right? If you're talking about motion of objects which are interacting gravitationally, right? It depends on the mass or the energy content of the objects. In very much the same fashion, but through a more complicated set of equations, right? The change in the universe, the expansion of the universe is closely related to the composition of the universe. What does it contain? What kinds of energy density does it contain? They are related through these equations put together by this famous man known as Albert Einstein. These are known as the Einstein's equations, all right? And it is them that relate, it's the Einstein's equation that relate the manner in which the universe is expanding to the energy content of the universe. So, our goal is to understand why we believe the universe is changing with time. In fact, it is expanding, as we mentioned. Okay? And from the expansion, or probably some other properties, can we understand what is the composition of the universe? Okay? That's our goal. You know this object here. Okay? What do you do? How do you know something is, the universe is expanding? How do you want to, in what manner will it manifest itself? Yeah, go ahead.
If you observe galaxies and other kind of celestial objects in the sky, you'll see that the light coming from them is redshifted, which means that they're moving away from us.
As simple as that. There will be you expect a Doppler effect if something is moving away. All right? So, that's why we are looking at spectra, right? If you have a hot body which contains many metals, okay, and you heat up the element, it will emit in a wide range of frequencies, all right? if there are very specific metals present in that body, it will emit at specific frequencies. Or if you have a hot object, opaque hot body farther away, and there is a cool gas lying in between the far hot body and you, okay, you expect some absorption spectra. So if you look at spectra of stars or galaxies, what will you have? You will have a variety of emission and absorption lines, and these are typical spectra of some of the galaxies that we see around us. There are strong emission lines and there are strong absorption lines, right? And a trained astronomer will be immediately able to say what these transitions correspond to. In fact, you may not be able to see, this corresponds to a doubly ionized oxygen transition associated with a doubly ionized oxygen atom, and so on. Many trained astronomers will be able to look at the structure of the spectral lines and say what is the transition that corresponds to. What astronomers about 100 years back did was as follows. They obtained the spectra of many of these nearby galaxies that I showed in the initial slide, and compared the spectra of these galaxies, farther away galaxies, with our own galaxy. And what do you expect? If, as was mentioned, if this is the spectrum in the source's frame, that is, I have some source and it is emitting a spectrum and I observe in this frame itself, all right? Then I have a series of spectral lines. I will have a series of spectral lines. But if this student is moving away from me and he is observing the same source, what do you expect? You expect a Doppler effect. And what will happen is that the entire spectrum, that is, if it contains multiple spectral lines, the entire spectrum will shift towards the red end of the spectrum. And you can define an object called redshift, which is essentially the difference in the wavelength to the original wavelength. This is what is redshift. And if it is redshifting, the Z, which we have defined as redshift, will always be greater than 0. Okay? And now, let's go back to these galaxies. What happened to these galaxies? This is the spectra of different nearby galaxies. The details of these galaxies does not play an important part in our story. Okay? What one finds is that if you look at a specific spectral line, this is a spectrum from a collection of stars in our galaxy. This is a spectrum from a galaxy which is slightly farther away. This is a galaxy which is even further away, and this is the farthest of these 4 galaxies. And what this horizontal red arrow indicates is the shift in a particular spectral line, okay, of the H alpha emission lines. These details do not matter. In fact, what you find is that the entire spectrum shifts towards the red end. The farther the galaxy is, the higher the redshift, the change in the wavelength. And there is always a redshift, which essentially means the galaxies seem to be running away from us. And what Hubble, about 100 years back, in the 1922, 1923, exactly 100 years back, what he did was as follows. He measured the distances to these galaxies and attributed a velocity. If they are moving, if they are exhibiting a certain redshift, and it is due to Doppler effect, using special relativity, you can determine the velocity of the galaxy. And he, attributed a velocity to this galaxy. Please note, I'm using a word like attribute. I will clarify this point later. Okay? He attributed a velocity to this galaxy and plotted it as a function of distance to the galaxy. Okay? And he found a linear relationship like this. Okay? And what he found was that there is a slope, there is a straight line, there is a slope. And what he found was as follows: 2 galaxies in the sky that are separated by about a megaparsec are moving away with respect to each other at a speed of about 500 kilometers per second. Let me repeat that. 2 galaxies which are moving away from each other, which are separated by a distance of about 1 megaparsec, are moving away from each other with a speed of about 500 kilometer per second. This is a much more modern Hubble diagram. Okay, notice this distance went to about 2 megaparsec, not very far away. Okay, notice the distance it has gone to. It has gone about 300, 400 times larger. This is a much more modern Hubble diagram. The same exercise has been carried out. What we have done is measure the distances to these galaxies, measure the velocities, in fact measure the redshift. There is no difficulty in measuring the redshift. What do? You take the spectrum, light from a faraway star, run it through a spectrograph and compare the spectrum with a spectrum from your own galaxy. And you can immediately see what is the extent or redshift. I will speak to you about measuring distances to these galaxies. Just give me a minute. And what I want you to note is a modern value for the Hubble, for this slope is 72 kilometer per second per megaparsec. You know, almost 100 years later, what we find is that the distances, if two galaxies are separated by a distance of about 1 megaparsec, they are moving away with respect to each other at a speed of 72 kilometer per second rather than 500 kilometer per second. I have two questions to ask you. Okay, the first question is, what is the dimension, physical dimension of the slope of this curve? Okay, that's the first thing. What do these values imply? Your question.
When we measure the distance between two galaxies, do we take into account that the distance might be from the past?
From the
past, like
it is always from the past.
Yes.
It is always from the past. Yes, absolutely. Absolutely. When you observe a galaxy which is 1 megaparsec away, right? You are, let us say you are observing a galaxy which is 3 light years away. You are seeing not a galaxy, a star. Okay, 3 light years away. You are seeing it as it was 3 years old.
So now when we get the data from one place which is 3 megaparsec away, one which is 5 megaparsec away, there might be that time before's image.
That is correct.
So how do we then construct the image?
So it tells us how the galaxies were at different times in the universe. And that helps us understand the evolution of the universe.
So at a given time, how should we construct?
Just hold on for a minute, please. Yeah.
So at a given time, then how will we construct the image of the universe when we have data?
Oh, we cannot do that. We cannot do that. So when I looked at the picture there, you are correct. You're correct. But the galaxies are not going to, it is possible that the galaxy may just disappear due to some strange reason because they are colliding and so on. But we are believing such strange things don't happen. And that snapshot of the universe, you are correct. When we are looking at a galaxy 1 megaparsec, 1 million light years away, we are seeing it as 1 million years old. When we are looking at a galaxy which is 10 million light years away, we are looking at it as 10 million light years old. But first thing is that the age of the universe is much, much larger. So, seeing 1 million versus 10 million light years is a small interval in difference in time when compared to the age of the universe. It's like observing you today and tomorrow. There is not going to be a significant difference, because your lifetime span is like close to 100 years. Okay?
So, the images we construct is from different periods of time.
As we receive the light, period. We don't have a choice. Okay? And yes, they come from different times. Yes. Sorry? What's the question? Okay, you are answering my question. Okay. So, firstly, I should say that I'm running well behind my, I have covered 1/3 of the slides. I was hoping to cover 1/2 of them. Okay. So, what I will do is that I will either skip some parts of the story and proceed. Okay. And complete within the 2 hours. Okay. You can ask all the questions you want. So, remember, I'll come to you. I'm just trying to remind everyone that there were 2 questions. I hope you appreciate the question that was asked. Okay. The light we see from the galaxies are not all from the same time. If the galaxy is farther away, we are seeing it as it was earlier. His concern was whether does that reflect a good, correct picture of the presence or the distribution of the galaxies. To some extent, yes, you will appreciate this when you get to know that the age of the universe is much, much greater than, a few million years. Okay? I'll come to that in a story. I'll repeat the question. I know you are excited. What I'm asking is, what is the slope of this curve? What is it? Exactly. Okay? I can invert that and get a time. What does that time scale tell me? Can you make an estimate? I will tell you, a megaparsec is about 10 power 22 meters. Okay? I believe so. You can Google it if you want. Okay? If that is the case, what is this time scale? They said this is velocity plotted as a function of distance, and there is a linear relationship. The slope has dimensions of 1 over time. Correct. What does it imply? It's early in the morning. You should be able to answer me easily. What does it imply? Let me help you with an image. Okay? Think of, you have galaxies, right? They seem to be moving away from each other. Someone has created this movie, right? And then you run this movie backward. What will happen? They will keep coming closer together as you go back in time, right? And it's seemingly at some very early time, they are all on top of each other. This time, this movie is, this argument has its limitations. I will just bear with me please, okay? That this argument has its limitations. I'll clarify its limitations. The time when seemingly all the galaxies were on top of each other is often referred to as the Big Bang. Okay? The galaxies were thrown away. There was an explosion. We don't know what caused the explosion. And the galaxies seem to be, thrown away due to some explosion. And you are seeing these galaxies running away from each other. But I want you to understand that we are not, in some center where everything is moving away. Everything is moving away from everything else. I will try to help you create a picture, create a picture of such an image in your mind, okay? Or a video in your mind. There are two numbers. There is also a number involved, which you need to calculate. What you find is that if you invert, you just said it has 1 over time or frequency. I can invert that number to get a time scale. That is the time when all the galaxies were on top of each other, right? And if you use Hubble's data, which is 100 years old, that time is about 5 billion years. Okay? Which is, strange because it is less than or comparable to the age of the universe, age of the Earth. Okay? So in fact, when Hubble came up with this data, there was such conflict. This was because of, poor measurement of distances of galaxies. It has since been corrected. That's a story, that's a lecture in itself. I will not be able to go into it. The modern value tells you that the age of the universe is about 15 billion years or so. Okay? Now I can answer your question.
Yes, sir. So, the age of the universe is around 15 billion years. So, if the universe was not expanding, we could be able to see things which were 15 billion light years away from us. But since it's expanding, won't that limit be much less?
Oh, it's a very complicated argument to understand what happens. You are naive because the universe is expanding. You can't just talk about time multiplied by velocity of light to see what is the horizon, what is the distance you can see. It's a little more involved. Okay, so I have to introduce some special relativity to do that. Okay, so we know the age of the universe. There are other reasons which doesn't permit us to see the universe beyond a certain point. I will talk about that as we proceed. Maybe you can ask this question again towards the very end of my lecture, and I will try to answer to the best of my ability. Okay? So I've already crossed the limit of my first lecture. I'll just take 2-3 minutes. I'm supposed to give you a few minutes break. I will take 2-3 minutes, complete some aspects, and then, I'm going to skip all these. So the manner in which you can think of the universe is as follows. One of the simple ways to think is you are on the surface of a balloon. You are limited to the surface of a balloon. Okay? And if I inflate the balloon, what will happen? You put dots on the balloon, which correspond to different galaxies. And if I inflate the balloon, what will happen? The distance between the galaxies will increase. So if I take a balloon and I mark a number, right? I mark a number. I can give a grid, right? I can use theta and phi. You're familiar with spherical polar coordinates? I can use theta and phi to mark a number. Let's say there is a balloon, there is a galaxy in the North Pole and one galaxy in the South Pole. As I inflate the balloon, do the location of the North Pole and South Pole change? No. Right? But does the distance between these galaxies change? Yes. Okay? So this is a very good way of imagining how the universe expands, right? But there is a problem. You will think, what lies outside the balloon? Is there something outside the universe? Does the universe end? Okay? So a more precise picture is, instead of creating a balloon, you think of a three-dimensional grid. You think of a three-dimensional grid, right? I associate, there is a, so I can't draw a three-dimensional grid, so I draw a two-dimensional grid, okay? Right? This is at time t1, and I attribute 0, 0, 1, 0, 1, 1, 0, 1. At a later time, the grid is like this. Okay? It is 0, 0, 1, 0, 1, 1, 1, 0, 1. What has happened is that this grid has expanded. Right? The grid has expanded. You have to visualize a three-dimensional grid. I can draw a three-dimensional grid. For simplicity, I've drawn a two-dimensional one. Now notice, just like the North and the South Pole, those coordinates did not change. This coordinates that I attribute to these points on the grid, they do not change. But the distance between them changes. And that is what one means by an expansion of the universe. Okay? And where does it end? We don't know. For all purposes, it extends to infinity. Maybe there is some finite universe. We haven't observed the effects of finiteness. Okay? So, now the last part I just need to explain before I stop is the following. Okay? You can read this, but I said that, these galaxies, the galaxies are located here at these grid points. At a later time, they are still located at the same grid points. But the distance between any two of these galaxies has changed with time. Right? And they change with time through something known as a scale factor A of t. Okay? It just tells you how the universe expands. I hope you understand. These grid points do not change. The universe expands with time. And that is characterized by this function, which is usually referred to as a scale factor. All right? And what we are trying to understand essentially is, how does this scale factor behave? Now, something interesting that happens when you study general relativity. The point is, on these large scales that I am talking about, the Newtonian gravity that you have heard of is not adequate to describe gravitation. I have to mix relativity and gravitation. When you write a Newton's gravitational force law, like what is the force law? F is minus some g capital M small m by r squared. You know the meaning of all these quantities, right? So when I move this object here, right, one mass here, the force is felt immediately. But that is not possible. That's not possible in special relativity. So, exactly. That is inconsistent with special relativity. So what Einstein tried to do was mix gravity with relativity. And that's what is referred to as general relativity. And I need to use general relativity to understand how photons behave in the universe, how universe expands, etc. One of the interesting things that you can do is you can show using general relativity that omega is 1 over A. I will explain. Okay? Omega is 1 over A. What is A? A tells you about the expansion of the universe. That is, if this is the distance between these 2 points, okay? This is the distance between these 2 points at time t2. This is the distance between these 2 points at time t1. Any 2 points, in fact. A at t2, okay, divided by A t1 is just dt2 by dt1. Is this clear? The change in the distance between any 2 points, right, is because of the expansion of the universe. So what happens is that if I leave a photon in the expanding universe, it redshifts. It loses energy. If I leave a photon in an expanding universe, it loses energy. You may ask, where does the energy go? Well, it goes into the expansion. Okay? And this is what we observe as redshift of galaxies. That I used Doppler effect to say that these galaxies seem to be running away. But that is not the correct explanation. What we observe is cosmological redshift. Let me repeat, if I leave a photon in the universe, it inevitably exhibits redshift, and that is what we observe as redshift of spectra of galaxies. As the photon travels from that galaxy which is 1 million years away to us, the universe has expanded. Because of the expansion, the frequency of the photon has, as A increases, frequency decreases, wavelength increases, and you observe a redshift.
Yes, sir. So you said that in this coordinate system, you have this grid. In this grid, the points remain fixed. I mean, the points remain relative to each other. The directions are the same, but the distance changes. So now let us take, for example, this water bottle, and let us take 2 points which are adjacent to each other. So the distance between those 2 points will increase. So shouldn't the entire bottle expand along with the space? So like that, you can extend the argument saying that galaxies themselves should expand.
Okay. So we are on the surface of the earth, right? My different parts of the body are experiencing the gravitational force. Am I being ripped apart? What is too small? The forces that bind me, thankfully, are much larger than the forces that cause. What causes a tidal force? Okay? In a similar fashion, the forces that binds galaxies together are much larger than the expansion. What has happened is that in the process of expansion, as the universe expands, something have collapsed due to the forces of interaction, and they have formed bound objects, and they are galaxies.
So as the universe expands, the binding forces move the particles closer to each other to maintain the distance.
There is a force which is expanding the universe. But what is happening is that if there are 3 particles here, right, 4 particles here, they are gravitationally attracted to each other. So what will happen is that they will come together, but the universe is expanding. That's how galaxies form. We will see that. Okay? And that local force is larger than whatever is driving the expansion, and therefore they remain bound. Okay? So I will stop here. We'll take a few minutes break, and the bottom line is that we have universe which seems homogeneous and isotropic. It seems to contain matter. It seems to contain radiation. It is expanding. We observe redshift of galaxies. That is why we concluded that the universe is expanding. But what I have tried to emphasize is that the redshift is not because of a Doppler effect, but it is because of the fact that the universe is expanding, and in a more complicated theory of gravity, which is general relativity, photons do exhibit redshift in an expanding universe.